Today we're going to talk about electromagnetism, the phenomenon whereby electric and magnetic fields can affect each other. In order to do this, first I want to recap a little bit and then build a little bit more on what we've already spoken about. To start with, we've already learned that magnetic fields can be traced back to the motion of charges. The simplest example of this is when we have current moving in a straight line, whether that's in something like a cathode ray tube or in just a length of wire. And as we learned in this case, the magnetic field kind of loops around the current, and we can use our right hand rule to figure out the direction in which it's going to loop. But what happens if you take this wire and bend it into some other shape, in particular like a circle? Now you might say, how is there going to be a current going through a circle if it's just like a circle? We could always put a battery in it if we wanted to, or we can actually sort of take a length of wire, bend it into a loop, and have the two ends kind of stick out, and that's where the current can be entering and leaving from. And on those two like straight ways coming out of the circle, those two lengths won't really create much of a magnetic field because they're very close to each other. The current is moving in opposite directions, and so their fields will essentially cancel each other out, leaving us with just the field created by the looped portion, or the circular portion, I should say. To figure out what the magnetic field created by this loop of current would look like, we can use the right-hand rule. So imagine sort of if the current over here is pointing kind of to the right, you would point your thumb tangent to the circle at that point, and you would wrap your hands around it because this section of wire will create a magnetic field that wraps around this wire. Likewise over here and likewise over here. And what you'll find, given that the current is going counterclockwise around this loop, that anywhere inside the loop, the magnetic field is pointing out of the page. Each section of wire will create a magnetic field pointing out of the page, and so together they'll add up to make a stronger field out of the page. Meanwhile, outside, the magnetic field will always pointing away from us. And so we can represent that magnetic field like this. And this should actually look a little bit familiar. It's a lot like the magnetic field created by a bar magnet. It's as if there is a north pole over here and a south pole over here. And the magnetic field lines wrap around from the north pole to the south pole. So this is the simplest example of what we call an electromagnet. It is something that creates a magnetic field like a bar magnet, but the magnetic field isn't created by the same mechanism. It's not a property of the material. It's simply created by passing current through a wire with a particular shape. Electromagnets are very, very useful because they can be turned on and off and made stronger and weaker. Whereas a permanent magnet, it is a magnet or it's not a magnet, or you can do a lot of work to demagnetize it or remagnetize it, but that's not really practical. So for example, fire doors are controlled by magnets. They are held open, usually, by magnets. And those magnets are powered. They are receiving a constant electrical signal. And that electricity is basically wrapping through wires like this. And when you cut the electricity, the electromagnets are no longer magnetic. There's no more current to create the magnetic field. And so when you cut power to these magnets, the mechanisms holding the doors open release themselves and they automatically close. So this is a safety feature. If power goes out, the fire doors close automatically. It's much easier to ensure that a safety mechanism happens by powering it actively, and only if something fails or is turned off, you deactivate it and then it goes into motion. Another example of where the electromagnets are used, they're really used everywhere. They're used in your earphones. They're used all over the place. But a nice example that people don't often think of are those giant magnets that you sometimes see in like a scrapyard. These magnets are powerful enough to lift entire cars or giant steel beams. And if these were permanent magnets, you would be able to maybe lift up the car or the giant mass of steel. But what do you do then? Now you just have a giant piece of metal stuck to a really strong magnet. It's going to be really hard to pry that off. This is kind of like a one-use thing, or only even a half a use. You pick it up and you can't put it back down. But if you use an electromagnet, you simply run current through it while you want to pick things up and hold them, and then you simply turn the current off, turn the power off when you want to release them. So these are really handy pieces of technology, and again, they're used everywhere. If you look around at almost any piece of technology that's any more sophisticated than like a toaster, there are going to be electromagnets in it. In order to make a stronger magnetic field, we can always simply put in more and more current. But there's a limit to how much current that we can put through a wire. Eventually, there will be so much current through it that the wire will heat up, and that will make it less conductive. It can maybe start melting, and those are problems that we don't want to deal with. So if we want to make a really strong magnetic field, but we can't just keep increasing the current past some limit, what we can do instead is, instead of coiling our wire around once, we can actually coil it around many, many, many times. And when we do this, we call the result a solenoid. And it's really just a coil of wire, and each full turn, each full loop creates a magnetic field equal to just a single loop of wire. And simply by adding more loops with the same current, I'll basically multiply the strength of my magnetic field. So this diagram is it's a schematic of how it works, but in practice, the loops are packed really close together. And sometimes there might even be layers of these. So there'll be like loops coiling around in the cylindrical pattern, but then it'll be many layers deep as well. So we can actually use that process to create really, really powerful magnets. And in fact, we can use it to make magnets much more powerful than any permanent magnet could ever really be. There's actually a third right-hand rule that we can use to very quickly figure out which side of a solenoid is behaving like the north pole of a magnet, and which side of a solenoid is behaving like a south pole of a magnet. And we do this by wrapping our fingers around the solenoid in the same direction the current is wrapping around the solenoid. So in this case, at the bottom, the current is going away from us, and at the top, the current is coming sort of towards us. And so what that means is, at the bottom, you should point your fingers towards the screen into the page, and then curl them around, and at the top, your fingers come back out of the page. And you stick your thumb out, and your thumb points in the direction of the North Pole. So the North Pole, in this case, is on the right, and the South Pole is on the left. Now here's an example that actually shows that, except everything is a little bit flipped. In this example, the current is coming in over here, and so at the top, the current is going away from you, and at the bottom, the current is coming towards you, and so you wrap your fingers around it in that same way, and then your outstretched thumb points in the direction of the magnetic field. So if the magnetic field is pointing to the left here, it means the magnetic field is going to leave the solenoid on this side, and the magnetic field lines point from north to south. Now you might notice, inside the solenoid, the magnetic field is pointing from south to north. That is true. It is also technically true in a bar magnet itself, and that's because of some kind of like the detailed structure of where the magnetic field of a bar magnet comes from. But the rule of thumb is that the north pole of the magnet is where the magnetic field lines leave the magnet, and the south pole is where the field lines return to the magnet. And again, this is the principle behind which all electromagnets work, whether it's the pickup in an electric guitar, or whether it's the piece of machinery that, or the mechanism that causes the membrane of a speaker to vibrate and produce sound. All of these are examples of electromagnets, and all that's changing is the current through them. In the case of a speaker, the way that you make a particular sound is you modify the strength and direction of the current in the solenoid to cause the magnetic field to like flip directions, and that attracts a permanent magnet and causes it to go in and out and in and out. And by modulating the current, both its direction and its magnitude, you can make whatever sort of vibration you want, including vibrations that produce sound. With the exception of some kind of like old-timey methods like gramophones, that's the word, that actually produce the vibrations by having a needle literally kind of go up and down over ridges and it vibrates. And then that vibration gets amplified. With the exception of those kinds of things, all the recorded sounds that you ever hear are created through this process. Whether you're watching a movie on your TV or in a movie theater or listening to music on your earphones, the source of the sound that you're listening to is a permanent magnet near an electromagnet, and the current through the electromagnet is modulated so that the permanent magnet vibrates back and forth in precisely the right way to produce the sound that you're hearing, including my voice right now. This is also essentially where magnetism of a permanent magnet comes from. Each atom has electrons that are kind of whizzing about around it, and we use the term orbiting. Now, it is like more subtle, more complex than just electrons spinning around in circles around the nucleus, but most atoms, there is no sort of overall motion of the electrons. For every electron that's quote-unquote orbiting in one direction, there's another electron going the other way, canceling out its effect. But in some atoms, like in iron, there is kind of a net orbital motion of the electrons. There is a net current around the nucleus caused by the motion of the electrons. And if you take a whole bunch of these little atoms, each of which is like a little tiny loop of current, and you align them together, their magnetic fields add together. And that's where a permanent magnet comes from. That's what a bar magnet is. It's a material in which there are countless individual atoms, each of which has its own little loop of current. And if you align it so that those loops are all sort of facing the same direction, then you get a bar magnet. Now, these are loops of current that don't have to be powered by a battery or anything. It's kind of intrinsic to the atom. That's what makes a bar magnet a permanent magnet, because it will simply exist without any input of power. In a typical electromagnet, you have to continue putting in power in order to continue making the magnetic field. There are some exceptions by making use of things like superconductors, but that's a whole nother story. If we go back to our previous example of the solenoid, and again, if we think about the example of a speaker, which is created by modulating the current through a solenoid to create a changing magnetic field to push and pull a magnet on the other side, where we're using an electric field to generate a magnetic field, we can go the other way around too. We can use a magnetic field to generate electric fields. For example, consider this solenoid. You can ignore the cylinder, but in order to make electromagnets stronger, often what you do is you place an iron core inside the solenoid, and then the magnetic field created by the solenoid magnetizes the iron core, and that magnetization creates a magnetic field in the same direction, and it makes an even stronger field. I also like it because it makes it a little bit clearer to see what direction the coil is coiling. Now, in this case, our solenoid is connected to an ammeter. There's no power source here, so there's no current in this device, but this ammeter will be able to measure current. Now let's place a magnet near end A of this solenoid. I've placed it here so that the north pole is closest to side A. It doesn't really matter. And I've drawn the magnetic field. Nothing is going to happen. The charges inside of the wire are not really going anywhere or doing anything, so there won't be any effect of this magnetic field on the charges inside the wire because the charges inside the wire are not moving, and only moving charges experience magnetic forces. So just by placing a magnet near this, nothing is going to happen. Now, what's interesting, and what hopefully you kind of picked up on from the simulations that you were playing around with, if the magnet starts to move, everything changes. We are not going to go into the details of physically why this happens. What about this changing magnetic field results in the effects that we're going to see in the galvanometer. Unfortunately, it's really complicated. Suffice it to say that this is one of the things that led to the development of special relativity. The concept of electromagnetic induction was actually inconsistent with some of the basic principles of Newtonian mechanics. So this is a really weird phenomenon. And we're going to talk about what happens, not so much about why it happens. But here's what happens. If I take this magnet and I start to move it closer and closer to the solenoid, the magnetic field through the solenoid is getting stronger because it's getting closer to the magnet, or the magnet's getting closer to it. And it turns out that when this happens, there is a current generated inside the solenoid. The changing magnetic field causes current to start to flow. There's no battery hooked up to this. There are no charges really moving inside the wire, but or there's no current flowing through the wire, I should say. But when I bring this magnet closer towards it and the magnetic field is increasing, while the magnetic field is changing, there is a current induced in the wire of the solenoid. And in this particular case, there is going to be an induced magnetic field in this direction, to the left. And the reason for that is as follows. It turns out that if you change the magnetic field within a region, that changing magnetic field will create an electric field that wraps around in a circular pattern, just like how current creates a circular pattern of magnetic fields. And that circular electric field will have a tendency to push electrons around, if there are electrons to be pushed around or other charges to be pushed around, in such a way that their own motion creates a magnetic field that opposes the change. So in this case, our magnet is moving to the right, which means the magnetic field, which is pointing to the right, is getting stronger. And as a result, the induced magnetic field is going to point the opposite direction. It's trying to basically keep the magnetic field constant. So since the external field is growing as the magnet comes closer and closer, the induced field is going to point the opposite way to try to balance that out. Once the magnet stops moving, then the induced magnetic field disappears. So again, if our magnet is moving to the right, and the North Pole is on the right side, then inside the solenoid there is a magnetic field that is pointing to the right and getting stronger. This changing magnetic field, in turn, induces a response in the solenoid that results in a magnetic field pointing to the left, basically trying to oppose the change in the magnetic field inside the solenoid. So since the magnet's field is getting stronger, the solenoid is going to end up creating a magnetic field to cancel it out to some extent. Now again, the magnetic field in the solenoid is created by charges moving around it. So the changing magnetic field causes a current to flow on the solenoid, and the current flows because of an induced electric field. So this changing magnetic field induces an electric field that pushes electrons, charges around inside the solenoid in the direction needed to oppose the change in magnetic field. So in this case, since the induced magnetic field has to point to the left, we can use our most recent right-hand rule, pointing our thumb in the direction of the magnetic field, wrapping our fingers around, and we can establish that the current through the wire is moving in this direction. And that's going to result in our galvanometer deflecting, maybe in this direction to the right. If we flip things around so the magnet is now moving away from the solenoid, then inside the solenoid, there is a magnetic field caused by the magnet that's pointing to the right still, but this time it's getting weaker because the magnet is going away. And so since the magnetic field is decreasing, it's going to induce a response in the solenoid that again tries to stop it from changing. And so since the magnetic field is getting weaker this time, the induced magnetic field will reinforce the existing one. So this time the magnetic field will point to the right. It's trying to stop the magnetic field inside of it from diminishing. So if the magnetic field is pointing to the right, it means that the current has to be flowing the opposite direction as before. So this time the galvanometer will deflect in the opposite direction, representing the fact that the current is moving the opposite way. So again, the induced current created by these changing magnetic fields will always result in a magnetic field that is trying to stop the change from happening. If the magnetic field is getting weaker, then the induced magnetic field will point in the same direction as that. If the magnetic field is getting stronger, then the induced magnetic field is going to point in the opposite direction of the original one. This is called Lenz's law. And it's a piece of a more rigorous mathematical law that allows us to actually mathematically compare these things. That's called Faraday's law. But since we're not going to go into the actual math behind it, we're going to stick with Lenz's law, which is really this idea that the induced magnetic field opposes the change in the first. Let's consider one more example. This time, let's imagine our magnet is flipped around. Now, the solenoid, the magnet is creating a magnetic field that points to the left inside the solenoid. And if our magnet moves closer to the solenoid, the magnetic field is getting stronger. And as a result, the induced magnetic field will oppose that. Since the original field is getting stronger, the induced magnetic field will point the opposite direction, in this case to the right. So as our magnet moves to the right, it induces a magnetic field that points to the right. And that is caused by the current that starts to run in here. And if I instead take my magnet away, the magnetic field points to the left, but it's getting weaker. So the induced magnetic field tries to reinforce it, and so the induced field points to the left. Now, I can also do things like, literally, right now the magnetic field points to the left, now the magnetic field points to the right. This is like not just reducing the magnetic field, but I'm reducing it and then I'm continuing to change it in the same sort of way, but in a negative sense. That will also induce a current. So if you flip a magnet around near a solenoid, you'll also cause a magnetic field. You'll cause a current to be induced in the solenoid or in the loop. Which will in turn generate a magnetic field that opposes whatever change happened. So just like we can use electric fields to generate magnetic fields, we can use magnetic fields to generate electric fields, which is evidenced in this case by the fact that current starts to flow. The change in the magnetic field causes the current by first inducing an electric field, which pushes the current around, which results in a magnetic field, which opposes the change in the first. It's a lot of steps, so it takes some getting used to. Now, this also has a lot of practical applications, and the previous example we did, changing the current through a solenoid to change the magnetic field created by the solenoid to pull and push a magnet, which is attached to a membrane, causing a speaker to vibrate and make sound. Well, this opposite process is how we record sounds. This time, what we do is we have a magnet attached to a membrane, and when you speak towards the membrane, the vibrations in the air cause the magnet to vibrate. And as the magnet vibrates, it causes a change in magnetic field through our solenoid. And that change in magnetic field induces an electric current through our solenoid. And that electric current can then be measured and converted into a signal, which is how we store the sound that was being measured. So this is how microphones work. An analog microphone directly, for example, if you're at like a concert, or if you were at a concert many years ago when they still used analog recording devices and speakers and everything. In some cases, they still might for quality reasons. What they're doing is they're speaking into the microphone, causing something to vibrate, a magnet to vibrate. That vibrating magnet induces an a constantly changing electric current in a solenoid within the microphone. That current can then be sent directly to an amplifier to make the current, bigger, and that can then be sent to speakers, which is what you would hear if you're listening to a concert, because most people can't sing loud enough for a whole stadium full of people to hear. So the way that we record and transmit and replay audio is entirely based off of this property of electromagnetic induction. It's hardly the only thing. Pretty much the entirety of our electricity economy is based on this. The way that we generate power is electrical power is based off of this principle. A power plant, most power plants use steam to spin a turbine. That turbine has magnets in it, and it spins around inside of a solenoid, and that spinning magnet induces a current in the solenoid, and that current is then sent out to the power grid, and that's what we use to charge our phones and watch TV and vacuum and anything else that you might ever use electricity for. Alternatively, in a wind turbine, it's wind spinning a turbine. Literally, that turbine has powerful permanent magnets attached to it, and it spins inside electromagnets, and the spinning magnet induces a current, and that's what goes to the grid. Hydropower, water is flowing through a turbine. Most forms of power generation we use make use of this. In fact, even simple motors like direct current motors and little more complicated ones like AC motors, they operate under a very similar principle. One thing that I need to mention is that what I've been saying, as I move the magnet around, the field inside the solenoid gets stronger or weaker. It's actually not just the magnetic field getting stronger or weaker that matters. What really matters is something that's called flux. Flux you can think of as like the amount of something that is flowing through some region. For example, the rate at which water flows through a pipe is a kind of flux. The rate at which the amount of wind passing through a window can be thought of as a flux. And it turns out we can treat sort of how many field lines are piercing through the cross-section of our solenoid as a flux. So for example, right now, you can see that there is only one of the field lines that I've drawn passing through this end of the solenoid. But as I move the magnet closer and closer, more field lines enter into that surface. So as our magnet gets closer, it's not just that the field is getting stronger, but more and more field lines are being squeezed into the sort of cross-section of our solenoid. Consequently, the magnetic flux is increasing. Right now, the flux is constant, the magnet is stationary, and if I move the magnet away from the solenoid, then the number of field lines piercing it is decreasing, and so we would say that the flux is decreasing. To give a better or a clearer example, let's consider a region in which there is a uniform magnetic field pointing to the right. If I draw a window, and here it's like a perspective view, so the window is kind of like oriented perpendicular to the screen, we can see that a certain number of lines are passing through my window. The more lines are passing through it, the more flux is passing through it. You can think of it kind of like wind. And if I make my window bigger, more wind can pass through it, so more flux would pass through it. Alternatively, if I made the wind blow faster, more wind would pass through the window, and that would also increase the flux. So the flux is a combination of the strength of the field and sort of how big the region or how much of a region the field is going through. Now I can also change how much wind flows through a window by turning the direction of the window. For example, on a windy day, if I open all the windows in a classroom, depending on the direction the wind is flowing, we might have a lot of wind, your papers might be blowing everywhere, or there might not be anything because the wind is kind of blowing parallel to the window. And so the direction matters too. If I rotate my window so that these field lines are kind of just going across the window instead of through it, then there isn't really any more flux through my window. The analogy to wind is really perfect because the concept of flux applies to both of these in the exact same way. The difference is that with wind, you literally have the motion of air that's physically flowing through something, whereas with magnetic fields, it's a little bit more abstract, but the analogies always hold. So if you always think of these fields as being like wind, where the field strength is like the speed of the wind and the orientation is like the direction of the wind, it'll work out. So again, if we go back to our previous example, rather than saying the magnet is getting closer so the field is getting stronger and therefore the induced magnetic field points the opposite direction to balance it out, I should really be saying the magnet is getting closer and the field is pointing to the left and the flux is increasing. And so if the flux is increasing, that means the induced field will oppose the existing field. On the other hand, if the flux is decreasing because I'm moving it away, then the magnetic field will reinforce the existing field because again, it's opposing the change. And direction does matter because again, if I go back here, right now there is no flux through my little window. If this window were literally just sort of a square of wire, there's no flux, nothing is going to happen. And in fact, I could delete my magnetic field entirely and there would be no induced current because even though the field changed, the flux through the wire loop didn't change because there was no flux because of the orientation to begin with. So when we get rid of the magnetic field, there's still no flux. But if instead I took this square loop or rectangular loop of wire and I rotated it, I would go from there being no flux because the field lines are all going past the window instead of through it, to suddenly now some of the field lines are actually going through it. And the more perpendicular the loop becomes to the lines, the more lines will go through it. And so just by rotating this loop of wire inside a magnetic field, we'll end up inducing a current through the loop that will oppose that increase in flux. So in this case, the magnetic field is pointing to the right. And as I rotate my window in this counterclockwise direction, the flux is increasing. So the induced field is going to oppose that change in flux. So it's going to have to create a field in the opposite direction. We're going to end there. And while very qualitative, everything we just learned is enough to understand the basics of most of the principles behind the generation of power, of electrical power that we use, as well as lots of other devices like the magnets in microphones and scrap yards and all kinds of other things. So what you are going to do from this is, based off of these principles, your next job is going to be apply this to understanding how electrical motors and generators work.